Good morning, grade 12 students. In this session, we're going to continue with our chapter 9, about the function of neurons, and we're going to move to the exercises of the chapter on pages 199, 200, and 201. So first, we're going to start with exercise 2. Exercise 2 is saying what? This is exercise 2. Exercise 2 is going to study the properties of a neuron. So we have the setup schematized in document 1 in this document, and a giant axon of a squid. Squid is an animal, it's a marine animal. It's called in Arabic بيسموه الحبار. Says the squid is going to be used, and we use a giant axon of the squid, as well as we use two recording electrode 1 and recording electrode 2. These are recording electrode ER1 and ER2 recording electrode. Here are the excitatory electrodes 1 and 2. And also we have the reference. ER2 is used as a reference here. And let's see what will happen in this experiment. So they put these electrodes on the surface and look what will happen. So the scanning is set to a slow speed and at time zero. So they scan this, and at time zero, ER1 is introduced into the axon. So at time zero, ER1 is introduced into the axon. We have electric stimulations of increasing intensity. So they have electric stimulations of increasing intensity, S1 less than S2, less than S3, less than S4, and less than S5. So these are the stimulating or the stimulation intensity or intensity of stimulations of increasing intensity. They are applied at different times at time 1, 2, 3, 4, 5, and so on. So the graph is shown in document 2 is obtained. So this is the graph that's shown in document 2. My work is going to be on this graph. So we have different phases for the graph. We have the letters A, B, C, D, E, F, G, H, I, J, K. These are different phases. So this graph is showing the variation in the potential difference in millivolt as a function of time in millisecond after applying the electric stimulations of increasing intensity. They said first part, they ask about the explain the tracing ABC thus obtained. So you have to explain the tracing ABC. AB, we don't have any potential difference. The potential difference is equal to what? It's equal to 0 millivolt. So here they are placed on the outside of the atom. Remember, when we place them on the outside, we don't have any potential difference. Even though we place both of them in the inside, we'll have no potential difference. The potential difference will exist when we have introduced the one of the electrodes on the internal side and one on the external side. Here we're going to have the potential difference. So here the tracing AB, there is no potential difference. Why? Because both electrodes, they are placed on the external side of the axon. While in BC, and it's mentioned in the graph, it's mentioned we have introduction of the recording electrodes in the axon. So introduce them in the axon, one of them in the axon, and the other will remain outside the axon. So here, the potential difference, it drops to the minus 70 approximately, minus 70 millivolt. So this can be explained that we have the resting potential of minus 70 millivolt. Why? Due to the introducing, due to the introduction of the electrode into the internal side, so one on the internal and one on the external, so this will lead to the potential difference. And if you remember, this was in the introduction, we started with this experiment. We did 3 experiments, if you remember. We placed first 2 electrodes on the external side. The needle of the galvanometer, it doesn't deviate, it stays at 0. Then we place 2 of them in the inside of the electrodes, so also the galvanometer, the needle will remain at 0. However, when we introduce one in the inside and the other in the outside, so this will lead to the potential difference, which is equal to minus 70 millivolt, which represent what? It represents resting potential. While this is the explaining the tracing ABT. So we did this. This is the first part, explaining the tracing of ABC. Part B, they said referring to recordings obtained due to the stimulation S1 to S5. So we have stimulations S1, S2, S3, S4, and S5. These are obtained. And what can you deduce about the properties of the action? First of all, ya Hassan, yeah, and I want from you not to, what can you deduce? I want you to interpret this. Start with S1. After applying S1 and S2, I don't know, you can add two together. I don't know how can you work this. I want you to interpret this, ya Hassan. Yeah, start. Interpret.
At the beginning,
No, no. Start immediately after applying S1. And even though you can add two together, you start here, from here. Forget the phase ABC, INSA ABC. Start after applying the stimulation of intensity S1 and then continue. Okay?
at the at the beginning of the experiment, the potential difference was minus 60 at S1.
Minus
As
60
time
at S1. Okay.
as time increased and remains constant, as time increased from S1 to S3,
Hmm. First of all, Hassan, أنت
and
عارف شو عم نعمل؟
then increased from
شو هن ال
minus
S1?
60
First of all,
till
before
plus
before we
30.
continue, Hassan,
Interpret.
Hassan, listen to me. Before we continue, احنا نعمل interpret. Great. So what are S1, S2, S3, S4, S5? What are these? شو هن S1, S2, S3, S4, S5? Yes, Hassan. What are these? S1, S2, S3, S4, S5. شو هيدول؟ أكيد مش spaghetti 1, spaghetti 2, سلطة 3. أكيد.
Simulation.
Thank you محمد. بس بدي أشوف حسن، أنا بروفيسور حسن. So هيدول S1, S2, S3, S4, S5, they are stimulations. So my work here is going to be in what? Interpret these stimulations. So after applying Hassan S1 and S2, there is no action potential, even though we have a small artifact, small hyperpolarization. But here it didn't exceed the threshold. So there is no action potential, there is no potential difference. So here we can deduce that S1 and S2, they are what? They are ineffective stimulations. So S1 and S2, they are ineffective stimulations. However, after applying S3, what happened? Yes, Selena. What happened after applying a stimulation S3?
An action potential was recorded for the first time
Yes.
of absolute 100.
Uh, about, we can say from minus 70 to about 30 to 100 millivolt. Yes.
This indicates that X3 is effective and effectively the threshold of excitation.
Threshold of excitation. Very good. So here we can say that S3 is said to be the first stimulation or the minimum intensity of stimulation, minimum stimulation intensity that causes the appearance of the action potential. So what do we call it? We call it the threshold of excitation. Let's move now to Summer. Summer, what do you think about S4? Summer, can you hear me? Okay, let's move to Rama. Rama, good morning. Oh my God. So let's move to another one. Rama and Summer, they have problem, I think. Let's move to Hadid. Hadid, good morning. Can you hear me? Hadid, good morning. Good, good. So we still have Muhammad, the last chance. Yes, Muhammad, good morning.
Yes, good morning.
Okay, great, great. I have silent modes here. Great. So after applying S3, Muhammad, Selena said that S3 simulation S3 is said to be the first intensity to cause an action potential. So said it's the threshold of excitation. What do you think about
Yeah.
S4?
S4 and S5 phases similar to S3, an action potential was recorded of amplitude 100.
Of the same
So they are
amplitude.
effective stimuli.
They
Yes,
are
they
they
are
are
effective
considered
stimuli.
as effective stimulation. Okay, that's it. So here, thank you, Muhammad. So while ER1 is still inserted in the axon, so you have ER1 is still inserted in the axon, and to better analyze the recording obtained by stimulation S5, the scanning speed is increased. So we increase the scanning speed, and the tracing in document 3 is obtained. So here they said identify the different phases of this graph by specifying the corresponding ionic phenomena. So ionic phenomena, here we have to talk about the Na plus channels and Na plus ions as well, and K plus channels and K plus ions as well. So here they want to import C, then they identify the different phases of this graph by specifying the corresponding ionic phenomena. First of all, we have started the stimulation at part at 0.75 millisecond. Here S5 was introduced or was applied if you want. So here first, what can you say about the phase AB? What is the phase AB? Phase AB, we don't have any action potential. So what do you think, Selena? What do we call the phase AB? Phase AB of the action potential, the phases. So what do we call the phase AB?
The resting potential.
The resting potential is equal to minus 70 millivolt in almost human, for example. So it's equal to minus 70 or minus 75 approximately. So this is the resting potential. So Muhammad, what do you think about the phase BC? What does the phase BC correspond to?
Hyperpolarization or depolarization.
Depolarization. Here you have to describe the phenomena. What happened here? We have increasing toward the
Uh,
positivity. So what happened
yes,
for which channel is open? Na plus or the K plus?
the membrane becomes highly permeable to Na plus
Na
and less
plus.
permeable to K plus,
So the internal will be more
causing
positive.
a mass, causing an inflow of Na plus
Very good. So inflow of the
to
Na plus inside the cell. This will lead to the decrease in the negativity and increase in
why
the positive.
intracellular medium becomes positive.
More less negative and it's more positive. Very good. Let's move to the phase CD. I think we have Ali Hariri. Ali Hariri is here. Good morning, Ali.
Good morning.
So what do you think about the phase CD here in the graph of document 3? What do you think about this phase? This phase corresponds to what? Which
Repolarization.
repolarization. So it corresponds to what? What happened during repolarization? Which channels do you open? Mainly
The
the
K
K
plus
plus.
channels, I think.
Okay, and the internal will become more electronegative. That's why we move back to the negativity. While DE, what do you think, Vadia? What do you say about the DE phase? DE it corresponds to what? We decrease below the resting potential. So what do we call this? Yes, Vadia, can you hear me? I think Vadia has a connection
That's,
problem. Yes,
can
I
you
can.
repeat the question?
What can you say about the phase DE? What does the phase DE represent?
The,
It decreased below the resting potential. So what does this phase represent? Yes, Badia. Mainly it represents what? It decreased below the resting potential. So it's the hyperpolarization. It's more than the resting potential. It's negativity due to the inflow of the K plus. They move outside the cell and decreasing the positivity inside the cell. So let's move to the solution of this exercise. So the solution of this exercise, exercise 2, when both electrodes they are placed on the surface of the axon, there is no potential difference observed at phase AB. This may be explained that there is no potential at the surface. When ER1 was introduced into the axon, which is the phase BC, we have a potential difference equal to minus 70 recorded between the interior and the exterior of the axon. So the interior is more negatively with respect to the exterior, and the difference minus 70 millivolt. Due to the absence of any stimulations tracing BC, it corresponds to the resting potential. However, if we want to move now to the part two talking about the stimulations. So upon stimulating the action of intensity S1 and S2, there is no action potential recorded. Here we have a small artifact. They are not considered as the action potential. So what does this indicate? I told you that I'm going to solve this as interpret this part. So what does this indicate? This indicates that the stimuli S1 and S2, they are ineffective and they are below the threshold of excitation. However, when applying the stimulation of intensity S3, the first action potential was recorded of amplitude about 100 millivolt. So what does this indicate? This indicates that S3 is the minimum effective stimulation. What do we call it? We call it the threshold of excitation. However, as the intensity of the applied stimuli increases beyond S3, so S4 and S5, as Muhammad said, action potential remains constant at the same amplitude, 100 millivolt. This indicates that S4 and S5, they are effective stimuli. From all that we have covered here, this can be deduced that the squid is excitable and it obeys the law of all or none. Either we have an action potential or we don't have at all. So it responds to the stimuli that is above the threshold, while it does not respond to stimuli below the threshold of excitation. So this can be explained that they have the same amplitude, so it obeys the law of all or none. Moving to part 3, the graph corresponds to action potential obtained directly after applying an effective stimulus at t equals 0.725 milliseconds. So AB, we said it's the time needed to start. So mainly it's the resting potential, which is minus 70 millivolt. So AB corresponds to the time delay. So time delay needed to reach the electrode, and it's equal to about 0.25 millisecond. This where the recording potential is the resting potential, as Selena said, minus 70 millivolt. BC is the depolarization from minus 70 to about 40 or 45. Here it differs not exactly. So during this phase, what happened? The sodium voltage dependent channels, they are the Ne plus channels, they open and they allow the inflow of these ions inside the cell. So this will be explained that the inside will be more positive and less electronegative, and this explains the increase in the potential difference in this case, and the potassium channels, they are closed till now. Moving to the phase CD, we have the repolarization going back to the negative. During this phase, sodium voltage dependent channels, they close, while the potassium voltage dependent channels, they open. So outflow of these potassium occurs, the intracellular becomes more electronegative. However, the last curve, curve DE, it corresponds to the hyperpolarization, increased in the negativity more than that in the case of the resting potential. During this phase, we have a slight outflow of the potassium ions, where potassium, they are closing but slowly. So we still have more potassium ions, they are flowing outside the cell. So the electronegativity in the inside of the axon increases more than that in the resting potential. So these nodes are very important. You have to know them. Already we covered them before. So you have to know about the resting potential, about the threshold of excitation. You have to know about the effective stimulation, ineffective stimulation, what happened during the phases of the action potential during depolarization, hyperpolarization, repolarization, and you have to know these nodes in details. So here we have the curve DE, hyperpolarization. During this phase, we have outflow of more potassium ions outside the cell, and this is slowly because the channels, they are closing slower, and this will lead to the increase in the negativity of the axon more than the resting potential. Moving now to exercise 3. Exercise 3, pay attention what will happen here. So exercise 3 is showing document 1 that represents a stretch receptor. This stretch receptor is connected to a muscle fiber. So here we have the stretch receptor that's connected to a muscle fiber of a crayfish. These are presented in document 1, where we have the dendrite, the cell body, the axon, and we have two microelectrodes, microelectrode B and microelectrode C. The stimulation is done experimentally by exerting a force. This is called the traction. They call it the traction intensity or traction force. So document 2 it shows the result obtained where A, this A, it represents the tracing recorded when we increase the stretching of the muscle fiber. So we increase the stretching. So here it's about 1.5 approximately. So here in the experiment 2, we increase to about 2. So here it's about 1.5 arbitrary unit, AU. And here we increase to about 2 arbitrary units. And here we increase it to about 3 arbitrary units. So we have increasing of the intensity of the stretching of the muscle fiber. Figure B, here in this one, B, we represent the tracing recorded on the screen of the oscilloscope when two microelectrodes, they are inserted to the cell body. So here we are showing the potential difference in millivolt in each of the experiment. So here we increase the intensity from 1.5 to 2 AU, then we increase from 2 AU to 3 AU. So we are observing the differences when we increase the intensity. So what will happen at the level of the potential difference when it was 1.5 AU, what happened? Here it's about minus 50 or minus 45, or it's minus, for example, 55. Here potential difference, it decreases to about minus 45 approximately, and then it increases here about minus 40. So as we increase the intensity of the stretching of the muscle, the potential difference, it increases. While here it's showing the frequency, how many times it repeats itself. So as we increase the stretching intensity, as we increase the intensity of the force, the potential difference will increase a little bit, but it's showing that the frequency, it codes the nervous message. So the nervous message is coded always by frequency and not by the amplitude. So here, analyze these recordings and what can you deduce concerning the genesis and the coding of the nervous message at the level of this receptor. So let's start step by step to talk about these in details. First of all, what do we have? In experiment 1, when the intensity of the traction force or the stretching of the muscle, it increases to about 1.5 AU. So first, in the first experiment, we have intensity of simulation was 1.5 AU, and it was constant for about 8 seconds. Where? Let's see here, which is in tracing A. So here in tracing A, it was constant for about 8 milliseconds. It was constant at what? It was constant at 1.5 AU. So here I don't work horizontally, I work vertically. So here I have to continue with the B and the C. So I'm going to work like this, and not to work like this. Some of you, they are solving the exercise, working experiment 1, experiment 2, and experiment 3. No, they are different experiments, but they show you that BA is showing the intensity of the force, B is showing the potential difference, and C showing the tracing recorded. So you have to work like that. This is the first experiment. And then this is the second experiment. And then this is the third experiment. So you have to work like this, not horizontally. You have to work vertically. So here we increase the intensity to 1.5 AU. And it was maintained for about 8 seconds. So it remains constant for 8 seconds. What happened? We have a hypopolarization. We have a hypopolarization decrease in the negativity of about 6 millivolt. It increases from minus 58 to about minus 52 or minus 50. So here in these questions, I'm not going to be so strict. So we have here slight changes. So maybe you're going to see it as minus 50. It's okay. It works because I don't give you exactly. But if in the question I gave you exact graph, you have to give the values exactly. So the potential difference decreases to minus 55 millivolt at the 8th second. So the result, we have 3 actual potentials of equal amplitudes of 80 millivolt were recorded in the tracing C in the axis between the second, 2, and the 3. So here we have about 3 action potentials. These are 3 action potentials of 80 millivolt. We are recorded here. These are recorded in tracing C. So what will happen if we increase the intensity of the stretching? In experiment 2, they increased the stretching intensity to about 2 AU. So in the first experiment, they were 1.5. Here we increase it by 0.5 to about 2 AU, greater than that in experiment 1, as I said. So we have hypopolarization, but this hypopolarization will be of larger amplitude. So it increases from minus 58 to about minus 48 or minus 45. It depends. And then to decrease finally to minus 52 at what? After 8 seconds. So here in tracing C, we have about 12 action potentials were recorded. Sure, we're not going to count them exactly, but here about 12 action potentials were recorded in this tracing C. So here, between the second 2 and the second 4 of same amplitude as in experiment 1 of about 80 millivolts. So all of them, they have the same amplitude. Here we have the amplitude of 80 millivolt, but here we don't have, we have about 3 or 2 action potentials. Here the action potentials, the number of the action potential, it increases, but it remains the same as the first experiment at 80 millivolt. While moving for experiment 3, we increase the stretching to about 3 AU, 3 arbitrary units. So what will happen? The the potential difference, it increases to about, let's say you can say minus 40 here, minus 40 millivolt between the second 2 and the second 5, and then it decreases to about minus 50 after 8 milliseconds. So here the potential difference, all of them, the action potential of them, they have the same amplitude, but the number of the action potentials in the tracing C, it increases in the third experiment. So when the stimulus of intensity of the stimulus increases above the 3 AU, the stretching increases above the 3 AU, and it's maintained constant. In tracing A, we have hyperpolarization, but this hyperpolarization, it's higher than those obtained in experiment 1 and experiment 2, where in experiment 1 it was 1.5 AU, the intensity of the stimulus, while in experiment 2 it was 2 AU. So in experiment 3 it was 3 AU. So hyperpolarization of higher amplitude than that in the experiments A and B. So here it slightly decreased with time, but it remains above the minus 48 millivolts in B. So this leads to appearance of high frequency of action potential. Sure, we're not going to count these action potentials, the frequencies. So here, maybe you can count these, maybe you can count these, for example, but these one, you can count them. They are about more than 40, for example. So you can't count them. You can say of higher frequency without counting them. So here, the frequency increases between 2 and 8. So this shows what? This shows that the amplitude of depolarization observed in B increases, and it persists for longer time as the intensity of the stimulus applied, it increases. So here, this will increase the number of the action potential recorded, while the amplitude, it remains above minus 48 millivolt. So here, the genesis, or the meaning of the genesis, the production or the innovation of the nervous message depends on the amplitude of depolarization and the cell body of the neuron, in which turn depend on the intensity of the stimulus. So here, intensity of the stimulus has the higher effect. So here, the nervous message is on the axon is coded by the frequency. Why? Because in the axon, all of them, they have the same amplitude of 80 millivolt. So all of them, they have the same amplitude in the action potential, plus 80 millivolt, but the difference was in the frequency. One of them, the first experiment, it's repeated about 3 to 4 times. The second repeated 12 to 13 times. And the third, when we increase the intensity, it increases above 30 and 40 times. So here, always the nervous message is coded and it's modulated by the frequency and not by the amplitude. Even though we increases the action potential or the intensity of the stimulus, this will increase the threshold of depolarization, but it doesn't lead to the and it decreases the amplitude of the depolarization, but doesn't lead to the increase in the amplitude of the action potentials. All of them, they have the same action potential amplitude, while they differ on only the frequency, how many times it repeats itself. So this is the aim of this question, to know that the encoding of the nervous message is coded by the frequency and not by the amplitude. So this is exercises 2 and 3. You are almost done. So exercise 2, they show you the effective stimulation, the ineffective, and you have to know the phases of the action potential graph, and you have to know what happens during each of the phases: hyperpolarization, depolarization, repolarization, and you have to know in exercise 3 about the effectiveness of the stimulus, and also the relation between the stimulus, the amplitude, and the frequency. And the nervous message is coded by frequency and not by the amplitude, as we studied before.